Hello, Dr. Wu. Would you like to introduce yourself to the podcast?
Sure. I'm Dr. Wu. I'm a professor of machine learning at Northeastern University.
Can you tell us about your primary research interests and the projects you've been involved in?
So I've done a lot of various things. On the theoretical front, I've worked on basically mathematically modeling neural networks. Um, I was the one that worked on trying to find a closed form solution for neural networks. And in terms of application, I've worked on predicting premature birth. So when a woman is pregnant, like when the baby's going to come, or if we're going to have some kind of complications. So stuff like that. Yeah.
Could you talk about some of the challenges that you experienced when you were trying to discover a mathematical model for these networks?
So, well, it took me maybe 3 years of research, constantly working on the math. So there's, trying to prove something that nobody has else has proven is not easy. So you're constantly searching for a way to solve some problem that nobody knows how to solve. So that in itself is pretty challenging.
Mhm.
And the other part, I believe, is actually loneliness, because because by definition, nobody else is doing it. So nobody really knows what you're talking about. So yeah, those are some challenges.
So, could you elaborate on what a closed mathematical form is for neural networks?
So with the neural networks, currently the way we solve them is through this process called gradient descent. And for the longest time, I was looking for ways that perhaps instead of using gradient descent, we can just automatically get the weights themselves. Depending on how much your viewers know about neural networks, currently you need to do gradient descent, and this could take a long time. That's why we need like GPUs to solve them. So I wanted to find a way whether you can bypass gradient descent and automatically get the solution. And that was what one of my research is about. Basically, it is possible.
That's really, really interesting.
Mhm.
You share some of the progress that you made in developing an alternative to gradient descent?
Well, that paper is actually already finished and published.
Oh, okay.
Mhm.
So I know for a fact that it's theoretically possible.
Yeah.
So, what were some of we haven't read the paper, but can you just give us a breakdown of how it went?
Yeah, so currently with neural networks, the standard structure is you have some kind of weight and then activation function, weight, activation function, and that's like a standard way of representing neural networks.
Mhm.
And the activation function, we normally use this function called the ReLU. You may have heard of that. So what I discovered is that if you just change the activation function from
Yeah.
ReLU to cosine and sines, then the closed form solution is possible.
Oh,
In
wow.
fact, it's very easy.
Wow.
Yeah. So with the research, what we were able to find is that essentially, the closed form solution, the weights, is what we call the kernel mean embedding. So you just calculate the kernel mean embedding at each layer, and that is your solution.
That's awesome. Yeah. And the next question that we had was, as someone who specializes in kernel methods, how do you bridge the gap between mathematical theory and practical machine learning applications?
So are you saying that because currently kernels are not being used as much?
Yeah.
Like what is okay? So kernels were pretty popular before neural networks, and ever since the arrival of neural networks, we haven't really use kernels as much because neural networks just work so well. However, in the recent years, they've discovered that a lot of the neural networks, they do work, but their fundamental math could be actually described through kernels. So I think kernels like kind of was forgotten for a while, but I do think eventually we do need a better way of modeling neural networks, and kernels will ultimately be the way. Like it will be the fundamental math that describes the neural network.
Yep. And also for like our listeners who may not be as familiar, you also describe what kernels are and just give like a basic overview.
So kernel, well, when you say kernels, most of the time we're referring to a kernel function. And a kernel function is essentially a function that takes two values and then outputs one value. So that's a kernel function. And with a kernel function, it kind of allows you to do a, well, how much would your viewers understand mathematics? Like how should I go into this?
Well, we're trying to like target to everyone, so just like give like a layman's overview if that's possible.
Okay, so basically, with a lot of machine learning, what you're doing is you're trying to find a function such that when you put an input in, it gives you an output.
Yeah.
So far, so good. Like self-driving car, right? You see a cat. So the picture of a cat could be the input, and the output would be the brake. You see what I mean? So in machine learning, most of the time we're just finding this function, and a neural network is just a way of representing this function. Now, with traditional kernels, is a different way of representing this function. So it's just a way of representing this function, and with kernels. What they do is they look at the function as a linear combination of multiple functions. So imagine you're saying you're looking for this target function, and this target function is you don't know what it is, but you think it's a combination of these other functions.
Okay.
You don't know what combination. You just think and you are guessing that it's these combinations. And what you want to do is find the exact perfect proportion of these combinations. Does that make sense? Like you're looking for a function, and you are assuming it's a combination of these other functions, and what you're trying to do is find the perfect proportion that adds up to be the target function. So kernels are useful because they allow you to not just use a couple functions, they allow you to use infinite number of functions, and you can combine them to find your target function.
Yeah.
Well, okay, yeah.
So so it's very powerful. You're not just using like 5 or 10 functions, and somehow some kind of proportion of them give you the target function. You're using infinite number of them. And when you're using the infinite number of them, essentially you can fit any function when you have infinite. So that's why kernels are really, really powerful. And I do believe they'll ultimately be the mathematical foundation that describes neural networks.
I have a question about the kernel structure itself. So you mentioned how you're taking an infinite set of functions and then finding one that works for that. Are there also several that work for that particular?
No, you're not looking for one. You're looking at infinite number of functions and some kind of combination of them when they add up together.
Oh, okay.
Gives you the target function.
Yeah.
Yeah.
Can there be sets of combinations that work for a particular problem that you're trying to solve?
Sorry, you cut out.
Oh, can there be different sets of combinations of functions that work for?
Yeah.
It's very interesting.
Yeah. So this is why. Have you heard of linear regression?
Yeah.
Mhm, yeah.
So are you familiar with the math with linear regression?
Yeah, like with gradient descent and trying to fit the line. And
Yeah. So you can picture a line is really just two functions. One function is x, and the other function is 1.
Mhm.
And then you're trying to find some combination like 5 times x plus 6 times 1. You see how that's the equation of a line, right?
Yeah.
So you're trying to find some combination of those two functions that adds up to the function you want. Now,
Yeah.
that's only 2 functions. Imagine when you have 3, 4 infinite functions.
Yeah.
So mathematics that allows you to do infinite functions will then essentially let you fit anything you want rather than just a line.
Yeah, I think that's a great way to explain it.
Yeah.
Because it makes a lot of sense to me now as well.
How like difficult is that to actually implement?
It's actually really, if you understand the theory behind it, it's really easy. In fact, on the YouTube, I give you a whole series of courses that you can just learn on your own. I mean, you would need to know calculus
Yeah.
Yeah.
to basically learn it. But if you know calculus, it's not that bad. So yeah, if you want, you're welcome to share the link with your viewers.
Yeah, absolutely. I think that could be very beneficial for them and even us to look at
Yeah.
deeper afterwards.
Yeah. So currently I post my lectures at university lectures online. So my machine learning 2 series is online. So I can share that link with you guys.
Yeah, that'd be
Thank you.
phenomenal.
So what kind of like neural networks have you applied these functions to?
So are you talking about just kernels in general or my own research?
I think like mainly your research.
Okay. So with my research, not only I discovered that closed form solution is possible. So when I say closed form solution, are you guys familiar with what I mean by that?
Closed form, as in like having just instead of gradient descent, you'd have like one function that'd be able to represent like the fit of the model or the fit of the network.
So the closed form solution is you have an equation, you calculate it, and that's your solution.
Okay, yeah.
Oh, okay.
Gradient descent is you make a guess and you incrementally get closer to that solution.
Yeah.
So you can see it's better if you just calculate the solution.
Yeah, absolutely.
Right. So that's what I mean by closed form solution. So in my research, not only did I find that you can have a closed form solution, you can also I mathematically proved that it's guaranteed to fit any function.
Oh, wow.
So it's guaranteed to give you the global output. That's how good the solution is. So it's not just good; it's like as good as it gets.
Yeah.
And we've tested this out with very, very complicated data. One, actually, let me see if I can bring. I might be able to show you guys a screenshot.
Yeah.
Okay.
You want to see a screenshot? If I can bring one up.
Yeah,
That'd be great.
absolutely.
All right, give me 1 second.
Of course.
Am I sharing the screen right now, or I'm not, right?
No.
No, not currently.
All right, let me try to do that.
Yep.
Share screen. All right, so you guys can see. So this is the paper I published.
Yeah.
You can see it, right? So let's see. Yeah. So this is an example. In this example, you can imagine that the hardest data you can possibly classify is just random noise. Like you have random noise, there's no pattern to it, and yet you can still find a way. So in this particular example, if you look at the chart on the left, you can see that the X and the circles are different classes.
Yeah.
And our goal is to find a function such that it's able to separate out these two classes perfectly. So that you can say, like, for this point, it is a circle. For that point, it is a cross. So what happened is, you look at the figure on the right, it basically shows the result after every single layer. So you can see this is obviously noise. So after the first layer, you can see that the cross and the circles, you can't tell them apart. They're just completely mixed together. And that's because they're noise.
Yeah.
So it's very difficult. And then at the second layer, you see there's a slight separation. And then we continue to deeper and deeper and deeper layer. By the time we get to the 9th layer, we found a function that is capable of separating the two data perfectly apart.
Oh, wow.
How do you guys, sorry to interrupt. How do you guys progress between the layers? Like, what exactly is causing the separation?
So what's happening is at every single layer, you're trying to find a function that pushes the samples that are in the same class compactly together, while pushing samples that are different class as far apart as possible.
Okay.
So if you can find a function that can kind of smoosh bunch of points that belong in the same class together while separating them, that's how you can tell them apart. And at every single layer, it's incrementally trying to do that better and better and better.
Wow.
Is it like a mathematical, I guess, way of like progressing between these functions?
Is there the mathematical way?
Yeah. Can you just like maybe elaborate like a bit on more like the math side of the functions and how like they get better at separating and smushing up the two different classes?
Okay. Well, so in terms of the network itself, the way the network works is that you put some input, you multiply by some weights, and then you pass through an activation function. That's what a single layer is.
Yeah.
Now, remember what I mentioned is that we traditionally use ReLU as the activation.
Oops, yeah.
Instead of ReLU, if we use sine and cosines as activation function, then you can automatically calculate the weight.
Yeah.
Okay, so there's an equation to calculate weight. So imagine you pass the data through the activation, you get the weights. You do that again, pass it through activation, you get the weights. You can do that over and over again. And I mathematically proved that if you follow through this trajectory, every single time you do it, you're improving the separation between data of different class.
Okay, yeah. Thank you.
So that is the idea is easy. Every layer you're kind of incrementally improving it, but why it actually works, you will need to read the math. Like you need to actually understand the math then to understand it.
Okay, yeah,
absolutely.
But you can picture if every single layer is slowly separating out the two classes, eventually you reach a point where in layer 9 here, they become separated. And in layer 10, not only are they separated, they're pushing the two classes as far apart from each other as possible.
Yeah.
Right? And then 11 is really pushing it apart. And at 12, all the samples in the same class are practically on top of each other.
Yeah.
Yeah.
So this is at that point basically reach the global optimum.
It's very cool.
So in this particular example, it basically shows you that this network is so powerful, even if you use random data, it will find a function that's capable of separating them.
Wow.
And then alternatively, instead of using random noise, in this example, what we did is we used data, we purposely made samples that are in different classes on top of each other. So they're supposed to be far away, but we purposely put them right on top of each other. And now we need to find a function that somehow separates them.
Yeah.
Yeah.
I don't know if you can tell from the figure here that all the cross and the circles, I put them really close to each other.
Yeah,
Yeah.
we can see it. Yeah.
Yeah. So in general, you can picture when you have data, you want to group data that's similar geographically close to each other in the same class. But in this particular case, I purposely, that's why I call it adversarial. I adversarially did the opposite. And I wanted to see if we can still find a function that is still capable of separating the classes.
Yeah. Yeah.
Hello, Neural Network listeners. Tune in next week to hear the rest of our interview with Dr. Wu. Armaan and Vasu out.